Yeah, I want to focus in on a specific aspect of ISS as an R&D platform for Mars. Talk to things that are near and dear to my heart, the environmental control and life support systems that we're going to need to go to Mars. The need for using ISS as an R&D platform is very real. We've had a lot of talk earlier today about the challenges we face getting the mass that we have to put into orbit down to a level that we can manage to run these missions. So we need to do some more work to reduce that launch mass. We're going to be away from home for a long time. We talked about the fact that these missions are in the class of a year plus to 3 years. And as was pointed out, unlike our situation on ISS or in any of the missions that we've run before, we don't have a viable abort short-term solution, and we don't have any viable way to get help from home. So that when we leave to run those missions, we're going to have to trust the technologies that we're taking with us to a very high degree. In addition, some of the things that have come up would say that there are areas where we don't really fully understand the challenge we're undertaking yet. And our work on ISS can help us a great deal in fleshing out those gaps in the challenge. The International Space Station is a great place to do this work. As has been pointed out, it gives us a microgravity environment, but even more important from my perspective, it gives us a reliably closed environment. It really is isolated from anything on Earth. And it integrates pretty much the full suite of systems and people that we're going to use on these missions. We don't get that in too many other places as well. A lot of the things that we've been learning already relate to the subtler aspects of the interactions with those people and those systems. And so this is an opportunity that we really would go to great expense and a great deal of uncertainty to try to replicate any other way than using ISS to do it. The other thing that it gives us, on the flip side of that, is a degree of flexibility and adaptability that is important to us. We have the opportunity to change systems, as has just been discussed, to make changes in the way we're operating those systems so that we can do the learning. We have the opportunity over time to add things to the ISS platform, to adapt it to our research needs. And it's close enough to Earth to where that's a practical thing to consider doing. We talked about reducing launch mass, and I thought it would be helpful to put up a couple of numbers that relate. If I look at the normal requirements that NASA's budgets, human support budgets would lay out for us and say, what would I need to support a long-duration space mission with the class that we're talking about in terms of consumables? So water and containers for the water, makeup gases, containers for the makeup gases, the food, the clothing, etc. Get some pretty daunting numbers up there when we think about where we'd like to put our total launch mass for the mission. Well, one of the benefits that we've already had from ISS, it's given us some ground truth. Folks have worked very hard on those consumables budgets. We've looked at practical levels of loop closure, the use of some of the systems that we flew with the Russian systems initially, with some of our systems. And the actual experience, given that level of control, is quite a bit better. There's still some pretty sizable numbers there. And these are numbers that would apply over the life of ISS per crew person year, up to the point when we launched our most recent equipment, the water processor, the OGA. That's about it. If we look at where we conceptually should be given those systems, if everything is working as promised, if we really can rely on those systems, we made a heck of a lot of progress. And significantly, one of the things that you see is that those budgets are now not dominated by the water. They're not dominated by the gases. They're dominated by what I need in terms of clothing, what I need in food. And those are very tough for us to change in the near term. So one of the takeaway thoughts here is that for these, I'll say, modest duration missions, where we're talking about a year to 3 years, we want to focus our attention maybe not so much on closing the loop further, but on making sure that the systems that we have are really mature enough and robust enough to where this is reality rather than design numbers. And the other aspect of it is this doesn't depict the mass of expendable hardware, replacement items, spares that goes with those systems. And those are areas that still have a lot of room to reduce that we want to work on. An interesting counterpoint to that, we talked about the radiation situation, the need to protect the crew against radiation. And as I read the literature, if I'm looking at this kind of class of mission, the least that we want to deal with is somewhere in that 10 to 20 grams per square centimeter shielding level. Those numbers are already low atomic number elements. So the logical thought is, if I compare these numbers, that material is probably pretty useful for me for radiation shielding if I solve the problem of dispositioning it right so it's effective shielding. And if I solve the corollary problem, saying once I'm done using it and I produce my waste products, I need to be able to stabilize and store it and disposition it so it continues to be useful to me for shielding. So maybe I don't really want to work on reducing the mass of those materials if all I'm going to be doing on the other end of it is adding mass to provide the radiation shielding I need anyway. The other piece of that that is really critical is the question of trusting the technology. We just talked about the need to make sure that the loop closures that we think we've achieved are reliably there on our mission. What we've learned in the course of the ISS program so far is that ground development certification, as we've done it, is absolutely necessary, but it's not really sufficient for the kinds of missions that we want to undertake. Most of the ISS environmental control and life support systems have had some kind of on-orbit growing pains. We found unexpected microgravity effects, unexpected system interactions, unexpected interactions with those messy humans that insist on occupying the space station, biofouling events. And we've had some areas where unknowns in the challenges to the environmental control and life support systems have contributed. The urine processor has had some difficulties associated with the fact that it's getting a lot more concentrated waste stream than was planned, than was in the design, and than was in the ground-based testing, because the crew's consumption of water has been reduced in space, concentrating their output products. There may well be some more subtle items coming in the challenges as we go along. We've also seen, if you look through the manifests that have been going up to ISS, that for almost every launch that's going up, the spares, upgrades, replacement items have been a major part of what we're putting up there. That points to the fact that we have a need to mature these items, to resolve that, and we also have a need to enhance some of these technologies so that we reduce their dependence on expendables. So the message is, maturation on orbit isn't an option, it's an essential item. We need to do research to better define the challenge. And since we keep finding that as we go farther, we uncover some things that we really didn't anticipate, we probably need to carry with us on these long-duration missions more than one technology to solve a bunch of these critical environmental control and life support systems needs. And that means we need to be prepared for remaining surprises. And there may well be some areas where we need to test on orbit and mature additional technologies beyond the suite that we're presently in the process of testing and maturing on the station. So, what might that look like? The busy picture. Key items, if you look down the left-hand area, there are a number of areas, but we may well want to introduce some alternatives, and we certainly have maturation to go. Humidity control, condensing heat exchangers have been working reliably, but they have an Achilles heel, an issue that goes on and on with biofouling that we certainly need to address, and we need to continue to mature and work those. Trace contaminant control technologies, probably some work to be done to reduce some of the expendables associated with them. There's the body A, the oxygen generation assembly. And we incur some new requirements as we look to these long-range missions in that area, because we need better answers for recharging high-pressure oxygen storage for the systems we're presently flying, because we will want to be doing a fair amount of EVA. We will want to be able to recharge high-pressure oxygen storage for emergency conditions. So we have to bring in some new technologies there. Water processing. We have a water processor assembly that is in the process of maturation, but has a relatively high expendables budget. There's probably a need to mature and develop some new technology to answer that. We mentioned the urine processor. What concentration technology do we use working that? And how do we work expendables reduction in all of those areas? Waste management, waste collection systems continue to be areas that are a challenge logistically in terms of reliability. They're dealing with some pretty difficult materials, some pretty difficult working conditions. And in addition, as I mentioned earlier, we really need to improve our ability to dehydrate, stabilize waste streams so that we can in fact store them, think about using them to solve that radiation challenge as we go. Fire detection and suppression, kind of the last item that I would highlight here. Developmental issue for the Orion vehicle. We need to make sure we've got a technology that will allow us to respond to a fire event, clean up the atmosphere, and not waste too much of our expendables if we have these long duration missions. So that's kind of the suite of what all the arrows depict. Top level is, first of all, that we have an awful lot of stuff where we are already hard at work using ISS as a test bed. All of those systems that are presently operational there are candidates for insertion, the maroon arrows, into a long-duration space mission. They have the potential to give us a pretty attractive performance in a lot of cases, and they are actively involved in an extended flight test program in the most relevant environment we presently can define. We have another one that is getting very close to readiness to launch. We've launched one of two packages already, and that's a test on an alternative carbon dioxide removal system, amine swing bed payload experiment. First part's already up there, which is the core element, the amine carbon dioxide removal module, and there's a balance of tests. It's a bunch of supporting equipment that is fast approaching the readiness for launch. So that will be one of the pathfinders for an ECLSS experiment flying on the ISS. Beyond that, new technologies from a host of these can flow into flight test regime and begin working maturation for deep space transit. At the same time, the introduction of those technologies can give us some very early insertion benefits to the space station. It can start to reduce some of the expendables, to reduce launch mass, which frees up dollars and launch capabilities to support the other experimentation that ISS really wants to do. It can start to free up crew time by reducing the maintenance burden, which again was cited earlier today as something that we really need to support the experimentation that we want to do. A little further down the line, we look towards surface systems. We almost certainly have another suite of life support, at least in some areas that we want to look at, because those systems will try to take advantage of in situ resource utilization. And as we've seen with the ISS system, the integration of that kind of system can be complex. The chemistry will be a little different you get out of ISRU, and so there's an integration test that needs to take place with those systems. Flows into maturation a little further down line, and ultimately the systems that we were maturing get inserted for deep space missions in the late teens time frame, which gives us what we need to support some of those early NEO missions that were talked about that are, again, part of the maturation for our planetary transport to Mars. And high pressure recharge gets inserted, and the ISRU-based systems get inserted in time for the big event going to Mars itself. If I take a cut at this in one other direction, you can look at some, say, top-level experiments that I think may be worthwhile to contemplate. And when we talk about doing these kind of top-level experiments, we start to tie into bigger questions, start to impact in a significant way what goes on station. Integrated tests of systems at the exploration vehicle conditions. Most of the design reference missions that I've seen are looking at exploration vehicles, surface vehicles, that operate at lower pressure than ISS currently operates, enriched oxygen atmospheres. Those will make a lot of differences in the way the ECLSS system works, in the way the crew functions, crew metabolism potentially. So there really is a need for extended duration integrated testing that starts to drive the maturation issue at those kinds of conditions. And that would imply the need potentially for an isolated experimental module suitable for long-term habitation, in which you would do both crew metabolic studies and ECLSS interaction. But taking advantage of the support systems that ISS offers, its proximity to Earth, the fact that we have safety bailout systems capable, actually tied to ISS, but operating for extended periods as an isolated environment chamber. You can add to that potential for long-term nutritional studies. Experience has shown that there are significant effects of human nutrition or unhuman nutrition of working and living in zero gravity. From what I've read, typically the crews don't consume as many calories as people really think they should. As we mentioned, water intake is different. There are going to be, and presumably are, but I'm not sure how thoroughly they've been studied, metabolic impacts on that, impacts of that then on the outputs of the human system, and impacts on their interactions with the environmental control systems. There's another issue here, which is for a very long duration mission, we will have basically no source of food other than what has been launched with us from Earth. So we have food stored longer than we typically are presently seeing it on the ISS. So that lends itself to another mission which logically might be combined, or another integrated experiment with your exploration vehicle conditions experiments, where you actually try to do a very long duration mission where you're dealing only with stored nutrients over a relatively long period of time rather than the current regime of makeup coming from Earth. And the question came up earlier, are we going to address centrifuge studies? And so far there is no mechanism for doing that, but there remains the question of, do I need centrifuge type partial gravity during a transient? The answer is probably no, but do I know absolutely that a transition to 3/8 G is going to stop the bone loss that we've seen? I'm not sure how solid the answer is. Do we have then an experiment here that should be done when we think about adding a centrifuge system of some sort to ISS? Might be a very worthwhile experiment. So there's an awful lot that we need to do. There's a lot that we're doing right now, but there are a great many things in terms of environmental control and life support research and development that can benefit from working with ISS. We've got a great opportunity. I'd really like to see us get to it.